A very good day to fellow judges and also members of the floor. My name is Christopher Janting Luchalu from Polytechnic Kuching, Sarawak, Malaysia. Today I'll be presenting my project on modeling and simulation of a direct ethanol fuel cell, electrochemical reactions, and mass transport considerations. So this is the content of my presentation. So what is direct ethanol fuel cell, DEFC? DEFC is a type of direct alcohol fuel cell that uses ethanol as fuel at the anode side in the cell, where it converts chemical energy into electricity and heat. There are few advantages of DEFC, such as low temperature operation and high energy density, so it makes DEFC a strong candidate for future portable power sources. Despite having advantages, DEFC also have a few disadvantages, such as ethanol crossover in the form of ethanol mass transfer, where ethanol from the anode side will travel through the membrane to the cathode side, and this reduces the performance of DEFC. And there are also some limitations in this DEFC, such as conducting experimental research can be costly, and also doing the experiment for the equipment are also unavailable. So there are alternative way to measure and verify the performance of DEFC and mass transfer in the fuel cell is by mathematical modeling. The objective of this project is to develop a mathematical modeling for DEFC based on electrochemical reactions and mass transport, and then to simulate and analyze the effect of operating conditions towards performance of DEFC. The scope of this project is using Butler-Volmer equation and also Fick law to develop mathematical modeling, and the mathematical modeling will be used to simulate with different ethanol concentration. Okay, so this is the schematic of schematic diagram of DEFC, where on the anode side, the ethanol will be injected in, and then on the cathode side, air will be injected in. Okay, so at the anode side, the ethanol oxidation shall happen, and on the cathode side, the oxygen reduction shall happen. This is the schematic membrane electrode assembly of DEFC. And this is the formula for the flux in the membrane electrode assembly, MEA. This is a flowchart of overall research, where firstly we develop the model, and then we simulate the model to produce the profiles for different current density, cell voltage, power density, and molar concentration of anode side. And then we analyze the data. So this is the assumptions to do this mathematical modeling. And the mathematical modeling is based on mass balance, where input minus output minus accumulation is equal to 0. And then the flux value depends on the diffusion coefficient and ethanol concentration. And then this is the Butler-Volmer equation to calculate the current density. Then we adjust the equation to fit for this DEFC research on the anode and the cathode side. So this is the current density for on the anode and the cathode side. This is the formula. So, and this is the ethanol crosses the pathway along the MEA. And this is the molar concentration equation to calculate the molar concentration. And then this is to calculate cell voltage. So this is the result and the discussion. So this is the ethanol concentration influence on DEFC performance. So as we can see here, the blue line is for the voltage, and also the black line is for the power density. So we use 6 different ethanol concentration, 0.5, 1, 1.5, 2, 2.5, and 3 molar of ethanol concentration. So for the voltage, the higher the current density, the lower the voltage of the cell due to activation of a potential. And then for the power density, based on this figure, the performance of the DEFC increases with ethanol concentration. The cell voltage increases with ethanol concentration due to increase of anode reaction rate. When the cell voltage increase, subsequently the power density increase. And then this is the comparison of experimental and modeling data for 2.5 molar of ethanol. Okay, so the voltage and the power density values are parallel for experimental and modeling. This shows that modeling can be used to predict and produce accurate like experimental method. The error percentage of voltage is 2% and the power density is 2.8%. Okay, so and then this one is for the ethanol concentration profile at different layers. For this one is the A is the diffusion layer. From this graph, the change in ethanol concentration is very small as if it is constant. This is due to no chemical reaction occurred at the layer. And the B side is the catalyst layer. The ethanol concentration for all molarity decreased greatly due to electrochemical reaction occurred between ethanol and oxygen. And the C is for the membrane. The figure shows ethanol crossover where ethanol concentration is slightly reduced when traveling through this membrane than to cathode side. The amount of ethanol traveled through the membrane is the amount of ethanol crossover. This is the ethanol crossover profile for all concentrations. So the higher the ethanol concentration, the higher is the ethanol crossover. As a conclusion, mathematical modeling is developed to determine the current density, cell voltage, and power density generated and amount of mass transfer in the MBA. The polarity curves showed that ethanol concentration does affect the performance of the fuel cell, such as the current density, cell voltage, and power density produced and mass transfer. The higher the ethanol concentration, the higher the current can be generated in DEFC, and higher ethanol crossover occurred. The voltage and power density value are parallel for experimental and modeling, which means mathematical modeling is reliable. So this is the references. Thank you for your attention.